Hello everyone, my name is Sinitsin, and today I wanted to talk to you about designing a read-intensive architecture for systems with high data through output. Let's think about terminology first. What you see here is a golden standard for modern read-intensive architecture. It's what you'll find in almost any big tech stacks. Kubernetes, where pods are moving constantly, and microservices, where logic is decoupled into domains. It's great for developer, but it puts a heavy tax on the network, and sharded and replicated storages, caches, and persistent layers designed for fault tolerance. In theory, as this scales linearly, if you need more, just throw more pods or nodes at the cluster. At a low to medium load, this works like a charm. But the magic disappears when you cross the 1,000 node threshold. That beautiful architecture diagram turns into source of pain. We hit a wall of system issues like tail latencies or protocol entropy, high contention, and topology drifts. Let's discuss them. On large scale, mean latency doesn't matter. In high load, we find a tail latency. Look at the fanout pattern on the right. To solve single query search, your service might pull 50 database shards. This is where slowest link rule kicks in. Your total response time is dedicated by the slowest shard in a bunch. At scale, those rare anomalies become your daily statistical reality. Scalability isn't free. There is a tax you pay just keeps the light on. Orchestration, a counterplane, and service discovery generate a massive event storm. CPU overhead of every node must track its neighbors. Protocols like gossip starts eating a significant part of CPU cycles. Network noise, management traffic checks, leader elections, grows non-linear. It eventually starts competing with actual user traffic. You might add 20% more hardware and get only 5% of performance boost. This attacks in action. Let's look at the math of resource death. Imagine n application pods and m cache pods. In starting setup, every pod opens connection pool to every cache node. With 1,000 application pods and 100 cache nodes, you suddenly have 100,000 open connections. This exhausts a file descriptor and creates massive connection for top of rack switch. The system literally chokes itself. This is the most critical chart for SRE, the latency with through output curve. There are three zones. A linear zone when load is low, latency is stable. A point of inflation where queues form. Latency shift from linear to exponential. And a saturation, this is the blast zone, where we hit the through output ceiling. Any tiny increase of load causes a catastrophic latency spikes. Our job is to keep the system in a linear zone with enough safety margin to absorb traffic spikes. When throwing hardware to the problem stops working, we use architectural painkillers like graceful degradation, circuit breakers, soft timeouts, and reading stale data. Yes, we just don't wait for our throttle resources forever. If the database doesn't respond within 20 milliseconds, just kill the connection. It's better to serve a partial response than a full response never. Once the painkillers are in place, we move to a physical segmentation. Multi-AZ or zonal is the concept is simple. We duplicate the entire stack across individual availability zones. Each zone gets its own microservices, load balancer, cache layers, and databases. The goal is a total fault isolation. If one zone goes down, the others don't. And the price is infrastructure overhead. You're paying for triple set of resources and a complex data synchronization. At this point, your dashboard might look great. Multi-Z is running, circuit breakers are turned, the system seems stable. But don't be fooled, this is an illusion of stability. We've masked the symptoms, but we haven't cured the disease. Our painkillers helped us survive the day, but they didn't fix the underlying inefficiency. To truly scale, we need to stop fighting side effects and start rethinking our services, how our services handle data at the lowest level. To move the needle on performance, we need to look inside the black boxes. In typical read-intensive systems, resources leak in three zones. Processing, we burn CPU cycle processing inefficient format. The runtime spent more time deserializing objects than executing a business logic. A transfer, a network is our toughest bottleneck. We waste bandwidth on redundant key and metadata repeated in every single request. And the storage, how data sits in memory dedicates its I/O and RAM consumption. Reading an entire row just to get one column is a luxury we can't afford. We need to make our data smarter and more efficient in all three states. In high loads, data formats aren't a matter of developer convenience. They are resources entry ticket for your CPU and RAM. How you pack your bytes determines how much actual work your processors can handle. Core optimizing levels are a binary over text. Moving your data from human readable formats eliminates overhead of parsing systems, syntax, and drastically shrinks payload. Zero copy access, utilizing the structures that doesn't require deserialization. By mapping data directly to memory, we bypass the CPU tags of creation and eliminate a garbage collection pressure. Physically skipping unnecessary byte. If you only need 3 fields out of 100, the system should only read 3, saving disk I/O, network bandwidth, and memory. Stripping schemas and field names from message body by using a central registry. The wire carries only the data. Optimized data isn't just about saving space, it's about reclaiming CPU cycles from infrastructure to power your logic, to power your business logic. Clean code and elegant abstractions are great, but the hardware doesn't see them. At high scale, your CPU only cares about data locality and cache efficiency. Grouping data into ETF objects is developer friendly, but it often results in polluted cache lines, forcing the CPU and load unnecessary bytes. Aligning data layout with the CPU physical architecture can eliminate cache misses and unlock a hardware's true processing speed. There's not a silver bullet. One pattern might excel in a random access while another dominates in a stream processing. Don't default toward standard. Profile, measure, and choose layout that fits your specific access pattern. We are shifting from byte level optimization to high level architecture. When your read load hits a wall, stop using the same data models in every process. It's time for secure. The principle is simple. Prepare data for task in advance. We take a single source of truth and generate a projection tailored for specific processes. Each projection contains only the field and format required by customer. No bloat, no overhead. So the format set, the structure is ready. Now we must move the data as close to the customer as possible. We are shifting from an external cache to caching directly within the pod's memory. So the benefits are zero network latency. In process memory, access is measured in nanoseconds, not in milliseconds. And resource efficiency, we have load a sharded cached cluster. But the challenge is if you cache everything, the pod will run out of memory instantly. So that type of caching is useless without smart routing. We transform our pods from identical copies into specialized data shard. We achieve this via three mechanisms: a service discovery, a real-time tracking of exact cluster topology, a client side balancing. The client selects the target node, eliminated unnecessary network hops, and a consistent mechanism, a consistent hashing to choose a right pod. It guarantees that request of specific ID always lands on the same node. This creates data locality. Each pod stores only its unique slice of the global data. And a final touch, the different formats in different storage tiers. What works on a disk is often poison on a CPU. We prioritize storage based on the environment. External storages like NoSQL or L2 caches, the priority are compactness and backward compatibility. We optimize for transfer size and storage volume. In process caches, see if we fight for every CPU cycle, we use large specific language formats native to your machine and runtime. We choose structures at the level that allow direct field access without parsing. For example, use flat buffers for transport, but transform them into native objects upon entering the pod, for instance, zero decoder access. The bottom line of this architecture marathon: economics versus risk. In classic setup, 100% of requests hit the external caches. In our target architecture, 85% is settled in the local cache, and only 1% ever reaches the database. This delivers massive resource efficiency. You need significantly fewer servers and drastically cuts your traffic costs. But on the other hand, there is a very complex system. We're trading simplicity for density. The system is harder to maintain, and packing the hardware reduces your safety margin during anomalies. Auto-scaling and monitoring now requires surgical precision. Yes, the system is complex. Every layer we discuss introduces new protocols and design risks. But this complexity unlocks the data density and performance that are simply impossible in standard hardware. So this architecture is a balance between survival and complexity. Before implementing this solution, ensure you're fighting the physical limits of hardware and not just suboptimal code. Thank you.